Hello and welcome to our webinar, Probing Sodium Channel Blockers in Vivo, TMS Strength Duration Metrics as a Translational Biomarker. I'm Tonia Smreczak, Managing Director of the Science Behind, and I'd like to kick today's session off with a short introduction to the science behind for those of you who are new to us. We're a specialist provider of neuroscience contract research services, bringing together a large network of neuroscience experts with our range of neuroscience technologies to support companies developing treatments and therapies for CNS indications and diseases. Working specifically on phase 1 clinical trials, our services enhance this early stage by providing information on how a drug impacts various aspects of brain and central system function. This deeper insight into neural mechanisms of action in humans serves to guide the development of new treatments and potentially enhancing prospects for success later on down the line. Today's webinar is an example of how these techniques we deploy can provide additional and valuable data to a phase 1 trial. And to present to us today, I'm pleased to introduce to you our speaker, Dr. Lorenzo Rocchi. Lorenzo is a consultant neurologist and neurophysiologist at the University Hospital of Cagliari, and assistant professor of neurology at the University of Cagliari in Italy. He's also visiting senior lecturer at King's College London. Lorenzo trained in clinical neurophysiology at the University of Rome Sapienza and completed his PhD at UCL's Queen's Squares Institute of Neurology, where he worked closely with Professor John Rothwell. His research focuses on the use of transcranial magnetic stimulation, EEG, and related techniques to investigate sensory motor integration, cortical excitability, and neuroplasticity in both health and movement disorders. He has authored over 100 peer-reviewed publications and serves on editorial boards for Frontiers in Neuroscience and Brain Sciences. And he has been working closely with the Science Behind since 2017 as a consulting neuroscience expert. Welcome, Lorenzo.
Hello, everyone, and thanks, Tonia, for the introduction. And so, as mentioned, this presentation is based on a recent article published in Epilepsia in July 2025, which is the result of a collaboration between our group and colleagues from University College London and King's College London. Epilepsy is one of the most common neurological disorders, affecting over 70 million people worldwide. It is characterized by a persistent predisposition to generate epileptic seizures with far-reaching neurobiological, cognitive, and psychosocial consequences. Epileptogenesis is generally viewed as the result of an imbalance between excitatory and inhibitory activity within neuronal networks, making them prone to excessive hypersynchronous oscillations. Epileptogenesis is an extremely complex process that remains only partially understood. As a consequence, the pharmacological landscape of epilepsy is vast, with numerous anti-epileptic drugs acting through multiple mechanisms and targeting a variety of ion channels and receptors. Among these targets, voltage-gated sodium channels play a central role. Many anti-epileptic drugs act as sodium channel blockers. Each channel has an alpha subunit, which is a large protein of roughly 2,000 amino acids, organized into 4 homologous domains, each containing 6 transmembrane segments. Sodium currents initiate action potentials, and the inactivation of these channels is crucial for regulating neuronal excitability. Several anti-epileptic drugs target these channels and are particularly effective in focal epilepsies. Carbamazepine, for example, binds preferentially to voltage-gated sodium channels in their inactivated conformation, slowing recovery from inactivation and thereby limiting repetitive firing. Lacosamide, by contrast, enhances slow inactivation of sodium channels, preventing them from reopening and helping terminate action potentials. These distinct kinetic effects make carbamazepine and lacosamide ideal candidates for comparative studies. Reliable in vivo methods to assess the effects of anti-epileptic drugs on cortical excitability are highly desirable for both clinical and translational research. Transcranial magnetic stimulation allows us to probe cortical physiology in a non-invasive way. When applied to the primary motor cortex, TMS elicits motor evoked potentials in target muscles. The amplitude of the MEP reflects the net excitability of the corticospinal system. Among TMS-derived measures, the resting motor threshold is the most common index of cortical excitability. It represents the minimum TMS intensity required to evoke an MEP of at least 50 microvolts in 50% of trials. There is a previous study which showed that both carbamazepine and lacosamide increased the RMT, which is consistent with reduced neuronal membrane excitability. However, because both drugs produce similar changes, RMT alone could not distinguish between their mechanistic effects. These results suggest that alternative measures are needed to investigate sodium channels function in greater detail. Our study, therefore, drew on measures originally developed for peripheral nervous excitability, which are essentially two. One is rheobase, which is the threshold current required for an infinitely long stimulus, and chronaxy, or the strength duration time constant, abbreviated with SDTC, which is the pulse duration needed for a current twice the rheobase. The SDTC quantifies how threshold current decreases as pulse duration lengthens, which reflects membrane excitability and persistent sodium conductances active near threshold, as well as passive properties like membrane capacitance. Conventional TMS devices cannot vary the pulse width and thus cannot measure the SDTC in the cortex. However, there are devices called controllable TMS, which is CTMS, and they enable precise manipulation of pulse duration and shape, allowing a detailed analysis of cortical excitability. Previous work has shown that by adjusting the pulse width, current direction, and M ratio, it is possible to target specific neuronal inputs to corticospinal neurons. So in this study, we performed a placebo-controlled, single-blind, repeated measure experiment with three conditions. One is carbamazepine 600 milligrams. The second is lacosamide 200 milligrams and placebo. All participants were healthy subjects. TMS measurements were taken at each drug's peak plasma concentration, supposedly 6 hours after carbamazepine, 1 after lacosamide and placebo. We recorded electromyographic activity from the first dorsal interosseous muscle with a bandwidth between 5 and 3000 Hz and a gain of 1000. Stimulation targeted the left motor cortex in all subjects and used three pulse widths, which are 30, 60, and 120 microseconds, always with an M ratio of 0.2, which is a conventional value. For each pulse width, we delivered 11 intensities ranging from 80 to 164% of the RMT. Log-transformed MEP's amplitudes were fitted into a sigmoidal input-output function to derive the RMT input-output, which is the motor threshold estimated from the input-output curve shown on the right. The model parameters included the midpoint intensity and the curved spread, yielding a smooth quantitative estimate of threshold for each pulse width. From these RMT-IO values, we constructed strength duration curves to model how threshold intensity varies with each pulse width. Using a least squares fit, we estimated two key parameters, the rheobase and the SDTC, as mentioned before. This approach directly parallels that used in peripheral nerve studies, providing a quantitative description of cortical membrane excitability. We analyzed the data using a linear mixed effect model, followed by ANOVAs on fixed effects to assess the impact of pulse width and medication on output variables such as the RMT-IO, the rheobase, and the SDTC. Given the known inverse relationship between rheobase and SDTC, we further examined this association using both mixed effect modeling and linear regression. So as shown in the charts, RMT-IO decreased with increasing pulse width and increased after both carbamazepine, lacosamide compared to placebo. However, the pattern differs slightly. For carbamazepine, the effect scaled with the pulse width, producing larger threshold shifts at shorter pulse durations. For lacosamide, the effect was more uniform across pulse width, suggesting a different underlying mechanism. About the other variables, lacosamide consistently reduced the SDTC and increased rheobase relative to both placebo and carbamazepine. As expected, individual SDTC and rheobase estimates were strongly and inversely correlated, as shown here, but this relationship was altered by lacosamide, which produced a shallower slope, indicating a change in the interplay between these two parameters. So to summarize the results, both carbamazepine and lacosamide increased DRMT, which confirmed a reduction in cortical excitability. However, the RMT alone could not differentiate their actions. By using strength duration analysis, we uncovered distinct pulse width dependent effects, which are as follows. Carbamazepine increased thresholds proportionally across all pulse width, but lacosamide effects were proportionally larger with longer pulse durations. Also, lacosamide reduced SDTC, increased rheobase, and altered their relationship, whereas, quite surprisingly, carbamazepine showed no significant changes in these latter two metrics. Let's move to the discussion. RMT reflects the membrane depolarization required for neuronal activation by TMS, which is a very complex process, influenced by both axonal and synaptic factors. Because these contributions are difficult to disentangle, RMT changes are often hard to interpret from a mechanistic point of view. By contrast, strength duration curves focus specifically on axonal membrane properties, offering a more direct window into changes in membrane excitability. Cortical SDTC is particularly sensitive to TMS pulse width, likely reflecting axonal membrane polarization and sodium conductance variation. Therefore, we know that SDTC can serve as a specific indicator of sodium channel-mediated modulation of cortical excitability. There are also computational models which support the view that axons are the main site of neuronal activation during TMS, which reinforces the relevance of SDTC as a biophysical marker of sodium channel function. So it is interesting to note that the effects of lacosamide on SDTC and rheobase mirror the findings in peripheral nerve studies. In those, SDTC changes following lacosamide or mexiletine, which has a similar mechanism of action, have been attributed to altered sodium conductance. Similarly, there is a report of accidental tetrodotoxin intoxication, which block sodium channels, which also produced characteristic SDT changes. So our results are overall consistent with the expected sodium channel blocking action of lacosamide. However, it is a bit more difficult to interpret why carbamazepine had no effect on rheobase and SDTC, which is an unexpected result, I would say. Axonal membranes contain sodium channels that generate both transient and persistent sodium currents, which, both influence SDTC though the latter, so the persistent currents, play a dominant role. Both carbamazepine and lacosamide are known to reduce these currents. However, it is known that carbamazepine induces a hyperpolarizing shift in the activation of persistent currents, and this has been shown in animal models to paradoxically limit its efficacy in suppressing the currents that determine SDTC. So this is one reason why possibly we did not observe modifications of rheobase and SDTC with carbamazepine. Another possibility pertains to a separate property of the sodium channels, which is their inactivation. Mechanistically, carbamazepine and lacosamide differ in how they stabilize inactivated states of the channel. Carbamazepine binds preferentially to the fast inactivated state of these channels, which delays the recovery, while lacosamide enhances entry into the slow inactivated state and prolongs recovery from it. So this latter effect fits well with our findings that lacosamide reduces STDC, as persistent sodium currents are particularly sensitive to slow inactivation. There are also other possible reasons, although not directly investigated here, because this is just a non-invasive study. Carbamazepine is also known to exert additional actions that interact with might obscure its effects on voltage-gated sodium channels. For example, it is known that carbamazepine can modulate GABAergic transmission, acting as a positive allosteric modulator of GABA-A receptors and possibly upregulating GABA-B receptors. At the non-invasive level, carbamazepine has been reported to increase the cortical silent period, which is a putative marker of GABA-B mediated phenomenon, although this finding has not been consistently replicated in non-invasive studies. So it is possible that such effects could mask or confound the influence of carbamazepine on sodium channel-related excitability. So in conclusion, we identified distinct effects of sodium channel blocking AEDs on the strength duration behavior in human motor cortex neurons. These findings support the use of strength duration metric as translational biomarkers of AED's action in vivo. And there is still a lot of work to do. This is just an exploratory preliminary study. And future work might test the specificity of these metrics by examining drugs which are not expected to affect sodium channel physiology, such as levetiracetam, for example, and also by developing other protocols, not necessarily TMS-EMG, but TMS-EG, for example, which are very useful to assess region-specific pharmacological responses beyond the motor cortex. All right. Thank you very much for your attention, and I look forward to questions and discussion.
Thank you very much, Lorenzo. That's all very, very interesting. Just going back to one of the, I think it's your second to last slide where you're talking about the additional neurotransmitters. Could you talk a little bit more detail where else can employing strength and duration curves uncover these distinct pulse width dependent effects?
You mean about carbamazepine or other drugs?
Other drugs.
Other drugs. Well, it's difficult to say because, studies on STDC and wheelbase are usually performed on peripheral nervous system. So the peripheral nervous system is quite simple compared to the cortex because it is quite well known that it is regulated by voltage-gated sodium channels, as I said. So that's the most obvious mechanism of action. So all drugs which affect that mechanism, like carbamazepine, lacosamide, lamotrigine. So a lot of different AEDs have I wouldn't say similar, but at least they partly share in activation of sodium channels from different kinetics. It is also possible with this STDC and wheelbase metrics to assess other components like potassium channels, for example. I don't think this has been done in the cortex, but there are hints that potassium channels can be tested in this way because they are responsible for some processes following the action potential, which is repolarization and possibly after hyperpolarization. So every drug which might target potassium channels might be interested in this in this kind of mechanistic approach. And the way I see it, these metrics might also be used as a negative confirmation of action. So I mentioned levetiracetam because it acts in a completely different way. So it should not have actions on sodium channels. However, one thing is in vitro and animal studies, another thing is in vivo studies. So the way I see it is also testing for drugs which are not expected to modify these metrics might be also useful to confirm it in vivo. So just, confirming its action and disconfirming it in vivo might be very useful, I think.
I agree. Have we got any questions from the floor? I know we've got another one sitting in the Q&A chat, but if anybody else on the call has got a question, please feel free to pop it into the Q&A section there. I'll just ask this one here. What axonal changes do you think surrounding cells such as astrocytes have on strength, duration, time constant?
Right. So this is a very good question. Short answer is I don't know. However, we should bear in mind that the metric we are using now is MEPs. Okay, MEPs are generating, as far as we know, from a very selected cortical circuitry, which is made of pyramidal cells and connections with inhibitory and excitatory interneurons. There are, I think, no data on animal models or cellular models which hints of, well, about a possible generation of MEPs by astrocytes. Okay, so I would say these cells are not directly linked to this kind of metrics as measured with TMS EMG. However, they might be linked in an indirect way because we know that they contribute to the buffering of potassium in the extracellular space. I think it would be a bit hard to disentangle these effects because they are indirect, but I cannot exclude that astrocytes, due to their buffering role, might be involved in these measures in an indirect way. However, this is it's not verified, so it's interesting, but it's not verified.
Great, lovely. Thank you very much. Do we have any more questions? Okay. Nothing seems to be coming up. Well, I'd just like to say thank you very much, Lorenzo, for your really informative presentation. And thank you everybody for listening to the webinar. This will be available on our website and on our YouTube channel on demand early next week, I believe. So if you want to go back to it, or if you have any questions later on down the line, please feel free by all means to contact us or reach out to visit the website for the webinar. On that note, I'd like to thank you all once again. Thank you very much, and enjoy the rest of your day.
Thank you. Thanks, everyone.
Thank you.